Okay, question 6.
This one's good.
Yeah, so
Interesting.
I have to delete it because I was taking so much time.
So when a trans butane trans 2, so 1, 2, 3, 4, then trans must be like that, right? Use the trans. First treat with peroxy, antifoam epoxide, and then at this stage we got CPBA, right? And then we get this must be again trans.
What's it called? Like the sleep time?
So, yeah, these two metal group must be trans after the epoxidation. So here, so it could be must be trans. Okay. So CH3. Or the other way. And then subject to the acid catalyzed hydrolysis. Acid catalyzed hydrolysis. So the OH group attack here. Then this bond will get broken. Right? So OH group. Acid catalyzed. Okay. OH group. So at the same time, let me see. And then if I say some acid catalyzed hydrolysis. As we have learned, these two OH groups should also be trans. These two OH groups should also be trans. So if this OH group is here, then this group OH group must be like that. The same thing, if this OH group if this OH group is this one, and the other OH group must be this. Yeah, well, then this bond is broken. After the reaction, these two are trans, these two are trans. So we can choose the one that match this. Surely this one match, right? This trans, these are trans. So this match. So these are trans, but these are cis. So this one is not right. It is not right. And this cis, this trans is not right. There must be this and this group must be trans. This and this group must be trans. So only the third one match. The two hydroxy group should be trans. So only the last one. So compound for question 7 is the same thing. The answer should be E. So these two hydroxy group must be trans. Why? Because according to the mechanism, is SN2 substitution. First substitution. and then addition. Addition of this proton from the acid. Okay. So long story short, these two always high hydroxyl group must be trans. So we choose that one. So only these two. And they should be equal amount, right? Because at the beginning there are two possibilities of attacking. Let me see. Yeah, attacking to the epoxide plane, right? There are two directions. So either this way or from either from this direction or from behind the wall. Two equivalent probability. So it should be equal amount. So, you look at this compound. Look at, sorry, I think this structure is very interesting. This structure is very interesting. So let's go back to see this structure. It may look very complicated. So we have this methyl group. We have this hydroxide group. We have this carbon. And then we have this carbon. So this means this bond is in this plane. Okay, this plane. I need to touch this one, otherwise it will black out. Carbon here. Over here. CH3 and hydrogen here. We need to keep in mind this is single bond. You can rotate, right? You can rotate. You can rotate. What I mean that here two-dimensional drawing can be very misleading. We cannot be misled by this drawing. We need to focus on the chirality, symmetry. So you can just imagine if I switch these two, the chirality change, right? Chirality change. So and then I switch these two. Okay, first I switch these two. Then beta group is here. OH group is here. And then I switch again. So I change twice, right? I change twice. Then the chirality does not change at all. So what it means that this structure and this structure are the same structure. And again, there is a symmetry plane, right? There's a symmetry plane here. This one, cut this into two halves, and they look the same. Therefore, these two must have opposite chirality. At the same time, it's a symmetrical structure, so this compound is methyl. It's a methyl compound. We have to play with that. You have to play this many times. Then you will get used to that. You see that? You switch. You switch twice. I mean, you switch two groups attached to the same carbon twice. I mean, you switch 2 out of 3 twice. You know, then the chirality does not change, because if it's R, you switch once, become S, and switch another, become R. If you start with S, you switch once, get R, and then switch another time, get S. So this compound and that compound are the same thing. And then there's a symmetry of plane. Cut this structure into 2 identical parts. Therefore, they have opposite chirality. So the whole compound is not chiral. Whole compound is not chiral. When it is not chiral, we call it what? It's not optically active, right? It's not optically active. So compound the structure. Question 8. Okay, question 8. Question 8. E, two pentane. E means what? Trans, right? Two trans. 1, 2, 3, 4, 5. Trans. With this, okay, then we react with MCPBA. Then we get what? We get this epoxide. And these two must be trans again. We'll put CH3, okay. And here we put C2O5. It must be trans. Or the other way. Okay, or the other way. They must be trans. Okay, because we start with trans, they must be trans at the end. So which one? So this one. This one match. And is enantiomers because these two are enantiomers. These two are enantiomers. Right? These two are enantiomers. Then you can see there's a mirror plane. Then look, mirror images of each other. This outer plane, behind the plane, outer plane. Then they have opposite characteristics for each chiral carbon. And then this is not a symmetrical structure, right? This is not a symmetrical structure. So there's no way for this structure to there's no way for the character to cancel. But even they're on the same side, they cannot cancel. Even they're on the same side, they cannot cancel. So if like that, only when it's symmetrical. You see that? If the structure is like this, then there's a mirror plane. Then they must have opposite character. You even don't need to figure out, to draw, you don't need. Because there's a mirror plane, they must have opposite character. And the character can cancel each other. But for this one, well, so they must have the same character, right? They must have, let's see, they must have the same character. Let's see, question, which one? Oh, we already discussed. Oh, Z. Oh, question 9 is Z. Okay, question 9. Question 9 is Z. Very good. Now we discuss this. So question Z, I mean there are C's, right? Then there must be C's together. So which one is C's? Oh, these two are C's. Okay, these two are C's. Then the answer should be A, and it's enantiomer. Again, here I repeat again. I repeat it many times, so I will keep doing that. You see that? For example, these are object here. CH3, okay. And this is related, okay. Here, if this is CH3. So what's the relationship between these two compounds, between these two structures? What are the relationships? What are the relationship between these two? Enantiomer? Again, they are the same compound. Why? There's a mirror plane here. They must have opposite chirality. Okay, if this is R, this must be S. Or the other way, this epsilon must be R. And then, if this is R, then you see that we switch for this carbon, we switch metal group and hydrogen. If this is R, this must be S. And if this is S, this must be R. So this RS, RS. Both of these are symmetrical structures. So these two compounds are the same. We don't judge whether they are the same by what? By their lookings. We judge the structure by their connectivity and chirality. They have the same connectivity, for sure. The atoms are connected in the same way. And they have the same chirality, RS, RS. They are the same structure. And it's a meso compound. And not chiral. And not chiral. We don't judge structures by their looking. We judge structures from their connectivity and chirality. They have the same chirality. They have the same connectivity. Then they are the same compound. And both of them are symmetrical. And the chirality of these two chiral centers cancel each other. The total compound, the whole structure, is not chiral. So for compound, for question 10, so yeah, this is peroxide. You see that COOOH, 3 oxygen is a very oxidizing agent. Then this is kind of peroxide. Okay. Peroxide. Then it can, the first step will get this. And then the second step is what? Is, we know, is a base, right? Then is a base catalyzed ring opening. Then the NH2 minus. Here we have H plus. The NH2 minus will attack the least substituted carbon. And when this substitution reaction, will attack this carbon, and then this bond will get broken. And this oxygen will carry 2 electrons away, make this oxygen negative. So this step will get this. So we get an oxygen minus here, and there's 2 here. And then this negative oxygen will catch 1 proton. So the answer should be C. The answer should be C. Okay. Here is base catalyzed, ring opening of epoxide. So, well, yeah. And here, yeah, so as we go, let me see. List the following column in order to increase the level of oxidation. So the higher, the more oxygen, the higher oxidation state. Why? Because the more oxygen can grab more electrons from carbon, right? That can increase the oxidation level. And then, but when there are more hydrogen, the carbon can grab electrons from the hydrogen. Right? So that will make a carbon less oxidized. So in order to list this, the increasing level of oxidation then is increasing level of oxygen. and decreasing order of hydrogen. So this one has this one has oxygen but has less hydrogen compared to this compound. Therefore, compound 2 should have the highest, followed by compound A, because compound A has 1 oxygen. And compound 3 does not have any oxygen. So it should be 2, 1, 3. The answer should be C. I'm sorry? Yeah, it's the increasing level, I'm sorry. So the increasing level, okay. So this has the lowest oxidation. So 3, 1, 2. Sorry, 3, 1, 2. So 2, 1, 3 is the decreasing order of oxidation. So likewise, you see, if we have more bromine, then we go back to the electronegativity table. Bromine has a higher electronegativity number than carbon. Therefore, bromine can take electrons from carbon. That make the carbon a higher oxidation state. If it is replaced by lithium, then carbon can grab electrons from lithium. That will make carbon less oxidized. So this is higher oxidized. This is lower oxidized. From the higher one to lower one, we get what? Reduction. Reduction. Because the oxidation state of carbon decrease. It's all about the electronegativity. You see that? Electronegativity. Kind of feeling 50% of the question can be explained by this electronegativity. 50% of question in organic chemistry can be explained by electronegativity, or maybe more than that. So, yeah, you see, for question 4, we can find this answer. Okay? We can find this answer, right? What is this? Is what? This is chromic acid. And we know chromic acid, now this is assignment 7. Question 4. Chromic acid can oxidize 1, 2, 3, 2. Okay, chromic acid can oxidize compound to what? To ketones and ketones. So this should be which one? So C. You know, if the OH group is here, if the OH group is here, it can be oxidized into what? Carbonic acid. So, but here is the tertiary. It's secondary alcohol. Then it can only be oxidized into what? Ketones. So question 5. So this is H. Right? And then this for, you see, this is reduction. And the LAH, lithium aluminum hydride, can convert this to what? To alcohol. So it should be OH. And this time won't change. That won't change. So this is a chiral carbon, because there's another hydrogen metal group. All these 4 groups are different, so this must be chiral. But there are 2 possibilities. Okay, there are 2 possibilities. It can be R, can be S, can be R, and it can be S. So it should be a pair. Should be a pair. So this one should not change. So 2 and 4 are wrong. If you look at these 2, okay. Yeah, you see they switch. So these 2 carbon must have opposite chirality. So both of them should be the product. Compound 1 and 3. So what's the answer? 1, 3. So should it be B? Should it be B? So for question 3, for this question, we can just go check our slides, PowerPoint slides, right? Under this condition, then this can only oxidize the compound to what? To aldehyde or ketones. Cannot oxidize. This oxidizing agent cannot oxidize alcohol into carbonic acid. So this can only be aldehyde. So should be this one. The answer should be D. Should be D, okay. And this cannot oxidize the double bond. So surely cannot reduce the double bond. Here is kind of reduction, so this must be right. This must be wrong, sorry. This can oxidize alcohol into aldehyde or ketones, cannot oxidize further. So we need to remember this, okay? We need to remember this. Question 7. Question 7. Which of these compounds can be reduced by sodium boron hydride? We learned that sodium boron hydride. Question 7. So sodium boron hydride is a weaker than lithium aluminum hydride. So weaker reductant. It cannot oxidize carbonyl group that is connected to oxygen. Cannot. Only this can. Let's see. LAH can reduce. And the sodium boron hydride cannot. Why? Because this is more stable. This is more stable. Carbon. This is carbon. This carbon is, R. Okay, we'll put R. R can be H. Can be heavy. Why? Because why this is more stable? Because you can just imagine, right? If there's, if it's just R, not OR, this can what? Have a equivalent resonance structure. They are resonance structures, so make this very stable. You see that? Make this very stable. Therefore, this sodium boron hydride cannot reduce that. Question 8. Which of the reagents below could efficiently accomplish transformation? Okay, oxidize. This. So A cannot, right? A cannot. Because A have two options. So if it is cold, then it can convert the double bond into what? Dihydroxy group, right? chromic acid. What about chromic acid? So A cannot. You know, A, you know, if it's cold, you will get this. Right? Can convert, can convert this double bond to this. And if it's hot, it can convert this OH to what? Carbonic acid. So none of them will work. Okay, none of them will work. And B, we know chromic acid can convert this to what? Carbonic acid. B not work, A not work. C can work, D can work. C can work, D can work. Oh, well, how long is that?